people really have this ability for flexible cognition. We can solve open-ended kinds of problems in a way that current models can't. We've got this Leabra model. There's this weird circuitry in the thalamus. What is it doing? How do we think about that? How are we going to incorporate that into our model? And then it kind of all started to fall into place with this idea that it might be doing the actual predictive learning. I think we're going to have AI that's conscious.
Oh, okay.
Everybody's going to be like happy to say, yeah, that thing seems pretty conscious. And again, I think that would be a situation in which we had essentially done a pretty good job recreating the human brain.
This is Brain Inspired.
How far along are we to building a functional and biologically mechanistic model of a brain? Some of us are farther along than others. Randy O'Reilly is farther than me, probably farther than you. Randy recently moved his computational cognitive neuroscience lab to UC Davis, but he's been working on his cognitive architecture Leabra since he was a graduate student many years ago. There are a small handful of cognitive architectures out there, big theory-based models that attempt to recreate large swaths of our cognition using various levels of inspiration from neuroscience and psychology. Most neurocomputational models focus on some singular mechanism, like how spike timing could drive plasticity, or they focus on some psychological function, like how we maintain some information in working memory. But cognitive architectures attempt to use overarching principles to assimilate lots of brain mechanisms and psychological functions into a unified whole. And Leabra, Randy's long-term attempt to simulate a human brain, is one such impressive architecture. So we talk about Leabra and how it started, some of the principles and ideas that drive it, and what he's currently adding to it. One thing he's adding is a thalamus, for instance, because Randy's done some recent work that shows that the thalamus may be important for predictive learning, among other things, which is learning by comparing our predictions about what's coming next with what eventually does come next. Randy calls this deep predictive learning and relates it to bottom-up and top-down connections from cortex to thalamus and back. So pretty important. So we talk about that and a ton more, plus a question from previous guest Anna Schapiro, who ruined the surprise, but I forgive her. Barely. You can run Leabra if you'd like. So I link to Randy's lab in the show notes where you can find instructions on how to play with Leabra and the free textbook that Randy and his partners wrote to go with Leabra. All of that's in the show notes at braininspired.co/podcast/88. If you value this podcast, the best thing you can do is to support it on Patreon. It's super cheap, and you get all of the full episodes plus bonus episodes, other bells and whistles like requesting guests for the show and submitting questions for the guests and so on. Go to braininspired.co and click the Patreon button there. Thank you guys for your support and for listening. I consider this podcast a celebration of ideas, and I'm glad to share that celebration with you. Here's Randy. So I have a memory of being at Phipps Conservatory 10 years ago in graduate school in Pittsburgh, Pennsylvania. I was walking through this exhibit of blown glass. There are these blown glass artworks shaped like plants and trees, and it was all very pretty and delicate. And I was thinking of you, Randy O'Reilly, during this time walking through Phipps, because I had I think I even applied to Boulder, to University of Colorado Boulder for grad school, and I'm sure I just got quickly rejected because of my previous academic performance. And I was thinking back how my life might have been different had I been in your lab. And now I have this memory of having the memory that at that point walking through Phipps of before I was in grad school. Can you just code that up in Leabra and tell me what's happening in my brain?
That's awesome. Okay, I just searched, and yeah, I see a email from you at UNC
No.
From 2005.
Oh, this is
We
embarrassing,
were working
man.
with Ben Philpott.
An excellent man. Gosh, please don't read it. I will definitely edit it out if you read it.
That's interesting. Yeah, small world. So the ability for cues to trigger memories is something we've really looked at in our model of the hippocampus. And so this idea that, you can have this integrated representation of different, situations, and the whole idea of episodic memory, of combining these, sensory cues. I'm kind of lost track of what I was going to say though.
Well, we're going to get into Leabra. I just want to know if you could code that up real quick and tell me what was happening. So anyway, thanks for coming on the show and talking to me. And thanks a lot for pulling up that email. Geez.
Yeah.
I'll have to ask you to forward that to me if I want to self-flagellate.
Yeah.
I remember, though, back in those days, being in awe of things that I was learning, kind of early in graduate school. How often are you in awe these days, just at the state of how far you've come, what you know, the ability of the brain and mind? Do you ever take the time, in the shower or wherever and just kind of have that sense of awe anymore?
That is a really interesting question because, our brains are wired to discount everything. And so I often try to tell myself that I should, get some kind of bigger picture perspective on things. And certainly, I'm in awe when I read all the work that's going on in AI. And so I think it's easier, to kind of confront new things quickly. And so when you see some new finding or some new result, or some amazing kind of new AI thing that happened, you can kind of get that instantaneous kind of derivative, right? That delta that says, oh wow, that's different. But for your own work, you just it's so slow, it's so painstaking, it's you discount it entirely, and it's almost impossible to have that perspective. So it's always, I think I lecture about this. That it's kind of this double-edged sword of it's what drives us onward, but it kind of deprives us of our, ability to kind of get pleasure out of things and it goes right back to the dopamine system, this whole idea that everything is relative to this expectation. It's an error signal. It's not the raw value. And so no matter what you do, how much you accomplish, whatever you think, you discount that. That's your expectation. And then everything is kind of relative to that. And it's hard to get those kind of, occasionally right when I come up with a new idea, which actually is often in the shower, right? Mm-hmm. You get that kind of, miniature burst of aha, here's something new. But a lot of times it's such a slow process that it's hard to get that kind of appreciation of I do have a declarative sense that, if ever I get kind of a bad review or which happens very frequently, or other kinds of disappointments, I have these kind of mantras of I am so lucky to be doing this. I get to do what I want to do. It's such an amazing opportunity.
You have to repeat it to yourself though, sort of.
Yes, exactly. Yeah. And, people interview for the lab, or, I talk to people and I get that you kind of get it vicariously. So people, when they first hear about what I'm doing, I have conversations, with random people, or just, when people come to interview in the lab and they're like, wow, that's so cool that you get to work on that stuff. And then I sort of I think, oh yeah, that is really cool.
Your mouth moves and you say, yes, that is cool. Yeah. And well, but you mentioned having that feeling when you get a new idea. And that's a really good example because I was reading Alison Gopnik the other day and just happened to come across her analogy of explanation or grasping an explanation to the feeling of orgasm. And
wow,
I know. Yeah. So this is a popular thing that she does. Yeah. Speaking of showers, no, I don't want, but that maybe we're wired to, for our, learning and motivation systems. And that's one of the things that, when we grasp something, it sort of co-ops the orgasm system, and maybe
Totally.
the new idea
Yeah.
is the same sort of thing.
Absolutely. No, I mean, I think, everything we do at some level has to be driven by our low level kind of dopamine motivational pathways, right? And so we have to have something that gives us pleasure for, achieving insight and learning, because we obviously are motivated to do that. And so, yeah, so I think it is, and if you think about capturing that in a computational model, this is, and I have thought about that, and it's really interesting, kind of like if you have a food, and it actually, when you think about it pretty deeply, there's similar kinds of issues. Like, we know you get a dopamine reward if you get some positive, like, food taste or something like that, right?
Mm-hmm.
But there is this kind of question of like, when does the dopamine come? Especially like if it's a meal, right? The meal is a protracted thing. And so like, when does it count? When do you actually sort of get the dopamine? And if you look at the, recordings of these dopamine neurons, it's like a little tiny bit of juice, and it's like lasts a millisecond or something. And so, you just get this kind of instantaneous burst. But like for something that's more protracted, or more complex, when does the dopamine come? When do you get that satisfaction, that feeling of satisfaction? And then if you take that same question and apply it to like, when do you understand something? And when do you know that you understand something? How do you know that you've actually understood it? These kind of metacognitive things that then also connect to the dopamine system. We think about that motivational stuff as being kind of hardwired because it's kind of, what drives the system. And if you could actually just kind of think thoughts and drive dopamine without actually doing anything meaningful, that would really short circuit the system. It'd be like doing drugs, right? So you would just be like, here I am sitting on my couch, and I just told my dopamine system to fire a bunch. And, it's like having an orgasm on the couch, it's like, wow, this is great, but you can't do that, right? And so what is it, how does our brain actually connect these kind of like more abstract, high level metacognitive things about like, what is it how do we know that we've done something or understood something, and then, that our low level dopamine system can actually reward us for that? And I think it actually does go back even for like meals and other kind of more basic low level type of things, this kind of question of when do you know you've done something?
My dopamine hit at the meal table comes after the European style, seemingly hour and a half that the family spends around the table waiting for the children to finish eating. I just realized also the understanding, the grasping, and that being a rewarding thing. My experience is really a series of realizing what I don't understand. So I'm not sure how that fits into the picture as well.
Right. Well, I mean, in some ways, understanding what you don't understand is more, or equal, if not more important, right?
Yeah.
And I think that famous quote, "It's not even wrong," from whoever that physics guy was. Pauli, I think, Wolfgang Pauli or something.
Okay.
I think it was him. And so like knowing precisely what you know and what you don't know is a prerequisite to sort of getting those answers, right? And it's kind of like, negative results in an experiment, or, finding something that doesn't fit with your theory or something. People think of that as like a negative thing, but it's actually, the most positive thing, because, if everything's just kind of consistent and kind of, you don't learn anything in that case. So yeah, I do think one of the big things, going probably a little bit off topic here, but
sure,
one of the big things that we're really thinking about in my lab right now is this kind of idea of like, the thing that makes us able to solve new problems is having that ability to recognize what we don't know. And to sort of to have, again, even like this kind of conscious metacognitive, however you want to describe it, kind of knowledge of like, okay, I know A, B, and C, but I don't know these other key points. And then kind of like what you need to do, right? And that knowing what you need to do, knowing the answers you need to figure out, allows you to then deploy like cognitive resources and everything to solving those problems. In any given situation, it's going to be different stuff that you don't know, different stuff that you know. And so that flexibility that we have to sort of solve new problems may be kind of tied up with this kind of ability to be aware of what we know and don't know. A lot of these current AI models are really struggling with this question of like, people really have this ability for flexible cognition. We can solve open-ended kinds of problems. We can do this kind of out of domain application of our knowledge in a way that current models can't. And so one idea is that, this ability to kind of have a metacognitive understanding of what we know and what we don't know is an essential part of that instead of just having like fixed pathways where information flows through neural networks and you represent pieces of information that in certain ways and it's kind of these kind of fixed pathways, that you do have this kind of introspective cognitive access, this metacognitive access to what you know and what you don't know. And then you can kind of say, okay, look, I can focus my now next steps of processing on this stuff, these questions that I've now recognized that I just don't know the answer to. And the other kind of piece of it is knowing the relationship. So, if I could just figure out what some particular mechanism is that connects phenomenon A and phenomenon C, and I could find that missing link B, then I could answer this question that I want to answer, kind of being able to represent the relationship among the knowledge that you have and where the missing pieces fit into that overall schema or relationships. Seems like, a really key element that we have that AI models don't have. And that's kind of like, how does that actually take place in neural networks? That's our big challenge.
That is a big challenge. Is that your existential experience of things that you don't know? I mean, my personal experience often is sort of just fumbling along, and then I seem to come across something that fills a gap, right? I don't like lay out what I do know and what I don't know in front of me and then can pick and choose what to study next. Sometimes it's that explicit, but most of the time it seems more I'm unaware of it. I'm metacognitively blind, perhaps, to it. But that might just be me.
Okay.
Unfortunately.
Yes. So I do think that is something, a lot of times when I start something, in a new area or something, it's very, like you say, kind of just fumbling along and you're just trying stuff. And I always have this mantra of like, start simple, start with success, just do something. And it's very much like this kind of, agile software development process or whatever. Mm-hmm. Instead of trying to plan everything out and figure out some kind of big logical structure, just like, get started and see what you can do quickly. That's just kind of my personality too, very impatient and sort of lazy or whatever. But
well, yeah, but it works.
Yeah. So I do think that it fits in with our kind of motivational systems that we want, incremental progress. We want those little bits of success and dopamine or whatever. Yeah. So I do think it is useful in general, despite whatever your personality is. But in those early stages, yeah, you don't even know enough to know what you don't know and don't know.
Yeah.
But I do think, and then you kind of accumulate. And then when you do get to that point where you can say, here's what I know and here's what I don't know, then maybe you're kind of pretty far along towards actually then being able to solve the problem, because it is, you're right, that it is like not the early stage, but the later stage.
You mentioned the thing that your lab is working on now, but your lab is working on lots of things and
millions of things. Yeah, one of the big questions we're working on.
So when we started off, you mentioned, being in awe of, seeing like whatever the latest AI thing is.
Yeah,
that's coming out. When you see that, when you read something like that, do you immediately think, I gotta build that into Leabra, or how can I do that? Like, I need to do that.
Yeah.
Is that your thought process?
Yeah.
That's no good.
Well, a lot of times it's kind of, how do I think about that? And what does this tell me?
Right.
A lot of times I will try to dig in and see, if I can figure out, what kind of lesson about, because I think my focus very much is on the kind of scientific question, not the engineering question. So I want to figure out, like, how does the human brain work? And so I see AI kind of stuff as like potentially informative for, what is unexpectedly powerful, what principles, really work, that we might not have thought about, and then how do we understand how those might function in the brain.
Mm-hmm.
So I'm always thinking about it from that perspective. And, like, for example, like generative adversarial networks, GANs,
Mm-hmm.
incredibly powerful, incredibly creative. I think they tell us a lot about why like social interaction is so important, because, it's this open-ended kind of interactive, I'm talking to my friends, they're talking to me. Both of us are kind of in a kind of, competitive, cooperative kind of arrangement where we're trying to impress each other, we're trying to outdo each other. And there's that kind of open-ended kind of interaction that allows us to sort of train each other, right? So our social interactions have that same kind of GAN-like property. But does that also operate in the brain? Is there a part of my brain that's like, talking to another part of my brain? And we do have this notion of like an actor critic. That's a well-established idea. That's kind of like what you see in these adversarial networks, but it is a really, I think to me, it's a question I don't have an answer to, but it's kind of still a question of like, what is it? They're incredibly powerful. I can see how social interaction can lead to those kinds of open-ended kind of, generative type of learning. And I wonder in the brain to what extent there is a thing like that kind of maps onto the GAN. I don't know yet.
Yeah, those are inspirational findings in AI.
Yeah.
This is a good time for me to play. So I have a question for you from a previous guest. So this is the other side of the coin, but this is Anna Schapiro. She was on episode 43.
Okay.
Hi, Randy. This is Anna Schapiro, and here is a question for you. What do you think are the most important aspects of the brain that are missing from current state-of-the-art machine learning models? So if you think about the problems that machine learning researchers are currently struggling most with, which of those problems do you think will be solved next if we take these elements of the brain into account?
This may be a question for later in the conversation, but it seems topical. So
yeah, absolutely. So thanks, Anna.
Awkward, isn't it?
I had to say in full disclosure that we were just meeting on Monday, and she mentioned that she was going to do that. So.
Oh, I'm going to have to. Oh, that is. You didn't plant the question, did you? Did you tell her to ask that specific question?
I would never do that.
I don't buy it.
Never do that.
Great, thanks, Anna. I go to great lengths. I always do it as a surprise. It's ridiculous.
Yeah, she just, she couldn't resist. Anyway, anyway, I hope I didn't get her in trouble. But so back to the question, though, I do think the thing we were talking about with the consciousness and the metacognitive access to your knowledge, to me, that is something that I can see being supported by the bidirectional connectivity in the brain. And so, there's these various theories of consciousness that actually have this kind of common element of kind of bidirectional recurrent connectivity, global workspace, integrated information, all these different kind of ideas that are all reflecting that same kind of core element of, this kind of plenary aspect of consciousness, that you have this sort of sense of everything being interconnected and talking to each other. And that is that same kind of thing about like metacognitive access, that you kind of have knowledge and that you kind of can take that knowledge and reflect that everywhere else in the brain and kind of operate on the knowledge, right? And this gets really back to ultimately to a lot of things that you see in these kind of more symbolic models, being able to operate on knowledge kind of as a thing that is really hard to understand in the brain. But I do think these bidirectional connections are a key element, and they're really missing in most of the AI models. And I have a particular bone to pick about this, which is a lot of the papers and everything talk about recurrent networks, and they're talking about these LSTMs, the long short-term memory machines.
Yeah.
And those, in the way that they've actually implemented them, are not the same kind of recurrent networks that exist in the brain. The brain's recurrent networks are these kind of massive bidirectional attractor dynamics. And these are the kinds of things that were very popular. Were talked about a lot in the 80s and 90s in the early neural network work that aren't what happens in an LSTM. An LSTM has a single independent neuron that has like a self connection of exactly one. And it's basically just like a kind of memory gate that can latch on to information and hold on to it. But it doesn't have any of this kind of attractor dynamic and this kind of sense that, you would have like a state of consciousness in your brain where all the different neurons would be kind of talking to each other. LSTM models don't support any of that kind of recurrent dynamics of that sort. And we think, we know from a lot of stuff like in perception and, lots of other cases, language understanding, everything, that like top-down influences on perception and language understanding and just everything are that kind of top-down bidirectional recurrent connectivity. And I think that existing models essentially don't capture any of that. So it's like a huge blind spot in the field. And the reason they don't capture it is because it's really, really complicated. It gets into these kinds of neural dynamics that unfold over time, and they get chaotic, and it just adds a lot of complexity to the models. And so this kind of existing paradigm, though, is really wedded to these very deterministic feed-forward kinds of activation dynamics. And again, even when they have recurrence, it's not true recurrence of this form. And so I think bottom line, current AI is missing dynamics. They're missing these kind of interactive bidirectional dynamics.
Okay. Well, at least current popular AI. I mean, the brain is so massively recurrent. And so like you said, there's these top-down projections, and that, we'll hopefully get into that with your deep predictive learning framework.
Yes.
But couple that with, local lateral projections that then feedback, but then you have to combine them in different amounts and different lengths, different synaptic traversing different numbers of synapses. And good God, it's messy. And I don't have a good picture in my head. I don't feel comfortable just saying, okay, there's top down and then there's lateral and they have different functions. Like I can't wrap my head around what might encompass all that. Do you have a principled way to think about that? I mean, I know you do.
Yeah, so I think about the lateral specifically is really important for inducing topology. Everything's, anytime you have bidirectional connectivity, there's a certain common element, which is this kind of mutual determination, right? That you have that really strong interdependence between the neurons. But if you want to make a distinction, the lateral stuff is really important for enforcing kind of the organization topographically of different representations of similar items are in similar parts in the brain. And that's probably really important for, just basic connectivity patterns. We know that connectivity in the brain tends to follow these kind of, neighborhood topographic kinds of wiring patterns. And when you have something as big as the actual brain, you really have strong wiring constraints. And so, the AI models have these really, massive convolutional type of kernels and have a similar kinds of biases because of those kind of convolutional kernel-like organization to organize things in these topographic ways. And so, I think of that recurrent connectivity as sort of, just sort of organizing the stuff to fit with the wiring diagrams that are the wiring constraints that we have to have in the brain. But the between layer bidirectional stuff is where you get the more interesting kind of really top down kind of, it's like I have a concept of what I should be seeing or hearing, and it really changes like literally what I see or hear. It's like you really get that kind of modal completion, like the Kanitsa triangle like pops out. It's not like it's just kind of like, oh, I thought I saw a triangle. It's like I see a triangle.
Right. Okay. Well, I won't bother you with the recurrence anymore because I know that there are those two main stories, but we'll move on. So I want to talk about Leabra. But before we get there, I know that learning is you consider one of the most important aspects of cognition, and I think it's really hard to argue with that. I had Tony Zader on my podcast, and he makes the argument that the vast majority of learning that we do happened throughout evolution and we're born with. And that
Right.
if you compare that amount of quote unquote learning, which is just evolution, he doesn't call it learning, it's evolution. I mean, you can kind of soup it up and call it learning. But that amount of
Right.
learning is much larger than the teeny amount that we learn to get us by during our lifetimes. Where do you land on this?
I disagree, because I think we have a huge amount of subcortical kind of evolutionarily wired kind of, again, like all the motivational stuff. There's a huge amount of stuff that we are kind of born with, and that is evolutionarily determined. But if you look at development, you get this really interesting kind of transitions where, as soon as the cortical side slowly starts to kick in, you get these amazing regressions where babies look like they're really good at recognizing faces, and all of a sudden they just fall apart. And that's because, the cortex is relearning everything from the ground up, I think. And I think, that's the kind of the core principle of like what, drives my research. And I think it's the core assumption that, I know I've had this conversation with Jeff Hinton and, various people who do, backprop AI type models. They motivate this thing by saying, look, the cortex is essentially a blank slate, more or less. There's you want to qualify that statement, but that the secret to human intelligence, so the story goes, is finding the learning rule, because it seems like we do learn the vast majority of what we know. And, there's so many examples, like, it's impossible for evolution to have enabled us to do reading and writing, because, that's such a short period of evolutionary time. That's a huge part of what we do. And just, the general, we don't know for sure, but it seems like our language and our culture and all the things that we've, that kind of make us smart are fairly recent, in evolutionary times, and most likely not something that, is just like coded up evolutionarily. So I think if you put all these pieces together and you just look at like, how does the cortex organize? How does it develop? It seems like it's mostly learned.
I mean, I think that there could be the case made for, mice, for instance, that don't need a lot of rearing.
Yeah.
Humans are, okay, so when we
Right.
talk about wonderful cognition, we're always talking about humans.
Right.
But, so Tony gives a lot of examples of like burrowing field mice, and how they're
Yes.
different and all
Yeah.
that. But humans also take a long time to develop, and we come out completely helpless, more or less.
Yeah.
So we might
totally.
be kind of a special case.
Yeah.
And so the learning,
Exactly.
the ratio might be higher for us than other lowly animals.
Absolutely. Exactly. And that's always, I think it's a fascinating question. Like, to me, like, again, I think it's easier to understand how we could come up with, just from a technology perspective, a learning rule, an amazing learning rule that like now enables us to learn, then to understand kind of like, given all that time of evolution, how can we capture that like now? Evolution is a very, very computationally expensive process. And so if we have to fall back on that, it's going to be like, it's too much work. So it's just not practical.
All right, let's talk about Leabra, shall we?
Yeah, sure.
So this is like your baby. I mean, one of your digital baby.
Yeah.
What's Leabra?
So it's basically, this project that I started back in grad school. And at that time,
I didn't know it was in grad school that you started it.
Yeah. And at that time, there was really this kind of sense that, there's, first of all, a lot of excitement about neural networks back then. And there were these different kinds of neural networks. And some of them were like Hebbian kind of self-organizing networks. And other ones were error-driven backrop networks. Okay. And so my feeling was, well, both of those things are really important kind of learning principles. Why can't we just put them together in a coherent framework so that we can kind of take advantage of both of those really important things? So so the original idea was just to put, self-organizing associative learning, which is another term for it that happened to fit with this acronym. So Leabra literally stands for learning in error-driven and associative biologically realistic algorithms. And so the project was to sort of just say, well, we can do associative learning and we can do error-driven learning, and we can put it together in a way that's biologically kind of plausible, biologically based. And so those are kind of my main themes that I have driven my research, throughout, is like, I want to know how the brain works, so it's biologically realistic. And I want to know how these learning principles operate. And so error-driven and associative. And then the whole kind of Leabra word is supposed to be like this balance, this process of balancing and coming up with something that's kind of integrating and balancing different forces, and not being kind of like extreme in only error-driven learning or extreme in only one way or another. And furthermore, as a metaphor, kind of also balanced at the level of analysis. So a lot of people think you have to do like fully biologically based models, like, really, really detailed computational neuroscience type models. Other people, like backrop nets, fine, we can be very abstract. And I'm trying to find that kind of middle balance again point in between. That's sort of, what does a really kind of reasonable job of capturing the biology, but also allows us to address these large scale computational questions. So that kind of balance point in the middle.
I mean, it seems like Leabra is full of compromises and allowing the constraints and compromises to drive. Because it's, I mean, the other thing is, well, there are 400 things to get to with Leabra, because it's become a monster, right? But you kind of have, it's a model of the brain at this point. I mean, did you start off wanting to simulate a human brain when you're in grad? Was that?
Well, that's always been my goal. Okay. Basically, if it's like, I want to figure out how it works, and to me, the technique to figure out how it works is to put it in computer code. And so, one definition of Leabra is whatever my current understanding of how the brain works is, pretty much that's what it is. But I think one thing that I've really taken to heart from, Alan Newell really articulated this principle early on, that, you want to have some kind of cumulative process in your development of computational models, that you don't want to be just like making random models of a bunch of different things, because then, you're kind of answering all these separate questions, but you're not really tackling kind of something more coherent that really builds a single explanation that can account for a really wide range of different data. And, the basic principle of, have the simplest theory, but no simpler, that accounts for the widest amount of data, is kind of the right criterion for thinking about what you want for a theory. And, a lot of times for any particular phenomenon, you can always come up with a particular model that does a reasonable job of explaining it. But if that doesn't also explain all this other stuff, then it's like, okay, well, how many theories do we need? So that cumulative approach has always been there. And so we do have a strong bias, in my lab to sort of say, well, if it's something we can explain with existing principles, let's do that, instead of just like cooking up a brand new model just to explain this one thing.
I mean, how often do you, when you're going to tackle a new cognitive function, let's say, and you want to use the principles that have now you've whittled a little bit over the years and have fit with 14 other cognitive functions, and you're going to add a new one, how often does it screw up the whole thing, and you have to either bring in a new thing or completely reinvent the learning function, or, whatever function that you're dealing with?
Yeah. And mostly a lot of the earlier work that we did was kind of basically saying, okay, look, we've got this vocabulary of mechanisms, and now let's go look at different parts of the brain, right? And so you say like the hippocampus, the prefrontal cortex, et cetera. And there, the idea is like, okay, well, within this common vocabulary, we have different parameters, and we can say the hippocampus is an area that, for example, has a really high level of inhibition. And so the representations are very sparse. There's certain patterns of connectivity. And when we put those things into this kind of common framework, it behaves differently in a way that fits with like this ability to do episodic memory. And so that's a kind of nice explanation that says, okay, well, different parts of the brain have different parameters. And so it doesn't really change the overall framework because we're kind of taking the same principles but applying it in a new brain area. But more recently, we have been doing kind of more of this, like, flipping over the apple cart or something, where we're adding these principles of like, how does the thalamus interact with the cortex? And this is something that was very much missing in our previous models. And now we have to say, okay, well, all this stuff that we were thinking about in one way was kind of only part of the picture. There's this kind of thalamic component to everything. And so now we're kind of revisiting a bunch of stuff to change how we think about what's happening there.
Well, the main brain areas, I guess, it's interesting because you talk about having main brain areas, but then, then you're adding thalamus. That was going to be one of my questions, because this deep predictive learning, the thalamus is pretty damn important for within that circuitry. I was like, well, he's going to be adding thalamus to Leabra then soon, maybe next, So, I mean, is that? So, but it's kind of started off with like 3 or 4 main brain areas, and then you keep like plugging a new one in. So, what are the main ones, and then we can go from there. Prefrontal cortex,
and so So in terms of so that and just to clarify, there's this sense of like these kind of more microscale principles. So like the idea of like, what do neurons do, and what do smaller scale networks of neurons do kind of in general. And then you have this kind of architecture level question of like, what are the different parts of the brain and how are they specialized, right? And so that's like the macroscale organization. And so at the macroscale, I think there's pretty solid agreement that like the frontal cortex is doing something different than like the posterior cortex. And so that's a big dividing point. And then, the hippocampus clearly is specialized relative to those other cortical areas. So the tripartite kind of organization into posterior cortex, hippocampus, and frontal cortex is very, very widely adopted and very clearly supported.
And you'd say that's the core of Leabra.
That's the core.
Okay.
If you want to understand cognitive level phenomena, you pretty much need those 3 players. And then, when you talk about frontal cortex, what we found is that you really start to need to involve the basal ganglia, right? So now, and this is the nature of how it goes, right? So you kind of like, you go down these rabbit holes and you're like, okay, well, if we want to understand how the frontal cortex works, what is that basal ganglia thing doing? It's densely interconnected. You can't really understand just the frontal cortex. You have to understand that system. And so in the same way, I think the thalamus, instead of thinking of it as like a module in the overall system, it's more like part of the posterior cortical and frontal cortical. It's basically part of all cortical networks. And so it's more like adding to the microscale rather than adding to the macroscale. And so that's a key point. Like, do you put thalamus as a macroscale player like the hippocampus, or is it a microscale kind of ingredient that's common across all these different areas? And that's more how we think about it.
Let's go ahead and talk about the circuitry and just the idea, because then we can bring it back to Leabra and how it fits in. Because there's the classical thing is the canonical cortical computation in the cortical column, right? And this is not that. Well, it's sort of that.
Right. It's sort of that. And so, once you start looking at the anatomy, it's actually remarkably clear, and that's great for computational modeling, that there's a real story to build on there, which is that there's layer 6. The deep layers of the cortex has multiple kind of sublayers, and so layer 6 is kind of the deepest of the deep, and it has these cells called CT, corticothalamic cells, that project down to the thalamus, and so once you start talking about the thalamus, you also then have to talk about the different lamina of the cortex. And so in the way we think about it, the previous models that we had been developing were all about the superficial layers of the cortex. So layers 2 and 3, which everybody, I think, pretty much agrees are kind of the main information kind of representation processing kind of areas of cortex. They're densely bidirectionally interconnected, and they have these pyramidal cells that, interconnect all the different areas of the cortex. And so they're the kind of main players in the cortex. And then you have these deep layers, which have in general, more restricted patterns of connectivity. And again, that what you said, the cortical column, you have a general topology where you have input coming in layer 4, it goes up to the superficial layers in 2, 3, and then it comes down to the deep layers, right, as kind of an output pathway. And then, what's interesting about the thalamus is that deep layer connection through the corticothalamic cells then goes back up. It's a loop, and it feeds back up into layer 4, and it kind of completes that whole circuit. Mm-hmm. So really, you have a kind of column level organization that involves all of those kind of cortical lamina and the thalamus in a loop. And that's why we think of it as kind of like, a kind of microscale thing. It's like a canonical architecture that exists across the entire cortex.
Does it get called canonical yet? Or because that's the word I was thinking as well. But
oh yeah, I think there's a paper from Shepard, maybe Sherman. I can't remember. There's Sherman and Guillory have the main thalamic paper, but somebody else called it a canonical cortical circuit.
Canonical thalamocortical. Something like that.
Yeah. So then you have to say, okay, well, what, it's like, this is always the challenge. Like, okay, you got all these different parts. What are they doing? Right. And that's really, I think, the key place where a computational approach can sort of give some insight. It's like, if you look at it from electrical recordings, the neuroscience says, well, neurons kind of have similar tuning curves in the superficial and the deep layers, even in the thalamus. So if you just kind of look at what are the neurons like firing at, mm-hmm. they're very similar. And so it's like, okay, what is it? And if you actually look at the Sherman and Guillory account, they kind of have a fairly vague story about like modulation, right? So that the thalamus, has this kind of top-down modulation mm-hmm. Of what's happening in the cortex. And that makes sense in terms of like attention. And so a lot of people think that one of the main functions of the thalamus is attention.
Just to back way up, the old story of thalamus is it's just a pass through for the relay, information,
the feed forward
relay to spread it around the brain. But that's changed in recent years, and so there's this attention story.
Right. So there's the attention story, and there's certainly a lot of evidence consistent with that you see these kinds of signals and deficits if you have damage to the thalamus, that you have certain kinds of intentional impairments. But, even then, it's like, okay, well, we needed all this extra circuitry just for attention, maybe not. And so that's where we started staring at the circuit and coming up with this kind of predictive learning story. Mm-hmm. And so I guess we can get into that.
Yeah,
now.
No, let's talk about it because I mean it's a beautiful story. So and it's a without visuals, it's a really hard story maybe to talk about. But
yes,
but the gist of it is that. Well, would you like to do the gist of it, or would you like me to do the gist of it?
Well, I'd be curious to hear your gist of it.
I'll give my gist of it. I mean, there's a lot of gisting, but. The gist of it is that like a lower area in, like, say, early visual cortex projects to the thalamus, and a higher area projects back to the thalamus, and they do so at sort of different see, I'm going to botch this from the beginning, like the relative importance of what to say, but they do so in such a timing that the projections from the early layers are these like really focal bursting projections, whereas the feedback projections from the higher area that come onto within the same circuitry in the thalamus are more of these lower firing but tonic kind
more
of
tonically active.
And so what happens is the way this all works is that the higher area, let's say V2 or later visual cortex, sends thalamus a prediction. And then the early area, the sensory incoming information, sends what the real sensory information is, what you guys call the outcome, in a very bursty way just after that prediction. And this all happens over and over and over at a cycle of 10 hertz. So every cycle is 100 milliseconds. And that's the sort of my gist of it. You can fill in the rest of the gist.
Yeah, exactly. That's great. That's awesome. So that's exactly it, that you're essentially constantly making predictions. and you're constantly getting kind of the right answer, the bottom-up sensory answer, and that you have a circuit that basically allows you to kind of represent the prediction and then represent the right answer. And then the temporal difference between those two over the thalamus is kind of the error signal that then kind of propagates back up into the cortex and trains up the cortex to be a better predictor.
The next prediction.
Exactly. And there is a large body of work over the many years thinking about how the brain might do predictive learning. And so the normal kind of default model for that, so to speak, the conventional model for that involves cells in the cortex that are kind of explicitly computing some kind of difference between a prediction and the outcome. And these models typically are based on Bayesian kinds of math. And it's nice because the Bayesian framework basically has a way of representing kind of a top-down expectation of an internal model. This is what you would expect to see. And then you get kind of the bottom-up data, and then you can kind of compare, did the bottom-up data fit with your top-down model or not? And so the Bayesian framework is a very natural framework mathematically to think about this kind of predictive learning idea. And so, most recently, Carl Friston, for example, has written a lot of papers, embracing this kind of Bayesian idea. But again, it goes back pretty far.
Mm-hmm.
Rao and Ballard are one of the most early, widely cited papers on this topic. And so we're basically offering a different way that the biology may support a similar kind of computational objective. And so instead of thinking about there being these explicit error coding neurons, you have this temporal difference operating over the thalamus that kind of codes the error. And an advantage of that is that nobody really has found solid biological evidence for these error coding neurons. Mm-hmm. that kind of standard approach, so to speak, predicts. And so it's a very, I think it's a really compelling overall computational idea that we learn by predicting, because it really answers this question of like, learning requires data. We know that it's a big data problem. You need constant sources of data to learn on, and the amount of quote unquote labeled data that we as humans plausibly receive is minimal. And so we need a bunch of unlabeled data to learn on. And how do you learn on unlabeled data? Mainly, you have to turn it into some kind of predictive or generative problem where basically your job is to encode and predict what's going to happen next. And if you can do that, you can then say, well, I've now learned kind of an internal model of the world such that I can actually predict what's going to happen next. And if I do that, it obviously has, survival advantages. I know what's going to happen. I can anticipate what's going to happen. I can behave in a way to avoid, negative potential future outcomes and, seek out positive ones and all those kinds of things. And so I think it makes sense, from a big computational picture that we want to be doing something like predictive learning. And so this model basically kind of just, very serendipitously, we just happen to be looking at this circuitry, thinking about, we've got this Leabra model. There's this weird circuitry in the thalamus. What is it doing? How do we think about that? How are we going to incorporate that into our model? And then it kind of all started to fall into place with this idea that it might be doing the actual predictive learning.
But hang on, because you could be looking at anything, any data, and say, we have this Leabra model, we could do X, right? So, I mean, there must have been some more intriguing reason to be looking at the circuitry of the thalamus.
Well, I mean, it's so important. And, it's like, anything, like, again, this idea that you kind of do research incrementally, you start with problems you can solve and you move on. We felt like, okay, we kind of understand, sort of, a lot of cognitive phenomena with this Leabra model, but, we're really missing this key part of the brain. Mm-hmm. And so it's kind of, we got to that point where we're like, okay, we've done enough with what we have. We need to really start to think about what's missing, what do we need to include. And the attention stuff really was an important motivator, because I think, attention also is a really important shaper of learning. And a lot of the problems also that we see in AI models, one of the big stories in the last few years is including more and more of these kinds of attentional mechanisms
Right.
to allow kind of like the same network to do many different things. And so like multitask learning, and learning without interfering with what you learned before, these kinds of things all really seem to depend on being able to sort of dynamically take the same network and kind of reconfigure it in different ways depending on what kind of task you're trying to solve. And that's basically attention, right?
Mm-hmm.
And so we originally started looking at it from an attention perspective, and then only kind of serendipitously started to see, wait, this could actually do this kind of predictive learning. So we really didn't sort of come into it saying, oh, we need a system to do predictive learning at all. It was just kind of looking at those driver pathway connections and saying, those are weird.
Uh-huh.
I mean, that was really the crux of it, is like, why is it that there's like this kind of one-to-one almost pathway where like the bottom-up kind of cortical areas are just like, driving these thalamic representations. It does, it just seemed like that's a very striking and puzzling kind of aspect of the circuitry. And if we could figure out how that would make sense, then maybe we would sort of see what the whole circuit is doing.
That's the whole Isaac Asimov, the interesting science happens when you say, that's weird.
Yeah, exactly. Exactly.
So you're talking about attention being a big story in AI. Backpropagation has been a big story in neuroscience. And you're like maybe the earliest cited example, your 1996 work on biologically plausible backpropagation in the brain. Then recently, maybe in the last, 5-6 years, we've talked a lot about how backpropagation might happen in brains on the podcast here. And so how does this, I know you tested it against backpropagation in the paper, and this paper is a monster, and it's a real delight. It's a chore and a delight to go through. But it's just super chock full of information. And so you tested it against backpropagation, and how does it relate to backpropagation? And I want to know how you think about, your early 96 work compared to like these days, it's the hot ticket to find backpropagation in the brain.
Yeah, absolutely. So one thing about that, first of all, is that that was one of my early things. I actually did that in grad school, and I'm really gratified that the current work that people have been doing has actually, recognized that original work, and so people are kind of saying, okay, this is one way to do it, and kind of, not all has been forgotten in the new is new. Everybody loves the new stuff and kind of forgets about the old stuff.
Oh, I think it's a very celebrated paper. So
yeah. So anyway, that's been very gratifying. And so the core idea there, just to summarize it, is that you have, instead of backpropagating kind of like mathematically, by going in the reverse direction down axons and stuff like that. So really kind of undoing or reverse propagating through the same kind of biological circuits, you just add a separate direction of connectivity. Again, these kind of recurrent connections that we know exist in the brain, the bidirectional connections that exist in the brain. And so the top-down flow of activity from higher layers to lower layers conveys error signals. And interestingly, the way that works most naturally in our framework is as this temporal difference. And this temporal difference actually goes all the way back to Jeff Hinton's original Boltzmann machine. That's where I, encountered the idea first, and I don't know where he encountered it, but
probably Steve Grossberg. I'll hazard a guess, but that's
probably Grossberg. Certainly, Grossberg has a phase-like top-down, bottom-up dynamic, so that's absolutely true. So you have to give credit where credit's due there. So anyway. Yeah. The idea that there is this kind of phasic difference that you can learn on is the core of that. And I just showed basically that if you just have these top-down connections and you literally take kind of the difference in activity when the right answer is kind of present at the output layer of this network versus kind of the answer that the network itself came up with, its quote unquote prediction or its own guess, then that difference over time is the backpropagation gradient.
Mm-hmm.
So these bidirectional networks essentially directly compute backprop, an approximation to backprop, but it's a pretty good approximation. And so, in fact, what's cool about this predictive learning thing is that it actually plugs into exactly that same temporal difference dynamic. And this is something we realized that we weren't very successful in the paper in kind of conveying, that essentially, the one way to think about it is we're just kind of plugging in the pulvinar, the thalamus, as a kind of output layer to generate error signals. But otherwise, it's just exactly the same principles of learning that we had talked about previously in terms of these backpropagation gradients in the cortex.
I mean, when you have thalamic lesions in the pulvinar, I'm really uneducated about the literature. Are there learning deficits of the?
Yeah, and the really interesting thing about that is that they would have to be very early for most cases.
Early cortex? What do you mean?
Early in development.
Oh, because you're already learned up.
Because you're already learned up.
Yeah,
exactly. And so most of the cases that we know about are kind of cases, in acquired, so to speak, strokes and stuff. And so there you see mostly attentional deficits because, the cortex is all wired up, So but a major prediction would be that if you did do like a neuroscience level, test in some animal with enough of a developmental window that you could kind of get it early and you would actually see learning impairment. So I'm very excited if somebody wants to test that.
And you guys talk about this. I'm sorry, I have a million questions. You guys talk about this in terms of V1 to thalamus and V2 back to thalamus, right? So kind of early visual cortex, but it's a principle that could just apply across cortex.
Absolutely. Totally. So it is, again, it's like this microcircuit kind of idea. It's something that would be present everywhere, and it is present everywhere. We know that these patterns of connectivity are present everywhere.
And you think it's the same canonical function everywhere?
Yep.
So one of the neat things is just the timing of all of this, because you can bring oscillations in and say it happens all within 100 milliseconds over and over and over. And it made me think, and I don't know if you guys talk about this, of whether if someone has a slightly faster alpha, if Bill has a slightly faster alpha than Jenny, what does that mean about their ability to learn? And I don't want to poor Jenny or poor Bill. Who gets the short end of the stick?
Yeah, exactly. So it's really interesting. So we actually looked at some of this. There's a data set that we had of people doing saccades in visual scenes. And we had electrophysiology recordings in posterior cortex. And you could really see strong individual differences in the timing, the phase relationships of these alpha signals. And you could see, the variability is not massive. So people do have pretty amazingly consistent 100 millisecond, 10 hertz kind of alpha overall. But, the precise kind of, there were definitely individual differences in the duration and also in the kind of phase alignment. And it was striking to me, even though there was a lot of consistency, there clearly were a lot of individual differences too. And so I really want to go back and see just exactly your question, like what is the effect of that? And, there's this idea that was very popular and very controversial from Paula Talal and Mike Merzenich, and the idea that developmental dyslexia and generalized language disorder, I forget what the right term is. There's a generalized language disorder term that I can't remember what it's called, but that those were due to timing, due to these kinds of differences in fine-grained brain timing.
Mm-hmm.
And it's controversial because they started a company and there was kind of commercial conflict, of interest type of issues in how they presented their research, and maybe some difficulty in replicating some of their results. There was lawsuits. But I do think that there's some core element to that just having these rhythms, if these rhythms are really driving our fundamental kind of learning processes, then it does seem like, little changes in that rhythm could really have some kind of effect.
I mean, there's a limiting factor as well, probably with how fast synapses can actually change. So if you can't go to
right.
1,000 hertz or something.
Can't speed it up too much, right? Yeah, exactly.
But at the same time, if you wait too long, your synapse might not be tagged or something, to actually change. You were talking about this dyslexia theory, and one of the things that you hearken back to in the paper is a 1991 Mumford theory about thalamus being a blackboard.
Yeah.
And I hear all the time these days that I hear neuroscience needs a lot of things, but I hear neuroscience needs more theory, less data. We have enough data. Now we need more theory. And and then I keep reading papers like this and reading about some theory that was 30 years ago, 40 years ago.
Yeah.
And that's now coming back and relevant again. And I'm just wondering, are the theories there but buried in the literature and just weren't paid attention to at the time? Or do we really need theory? What do we need,
Yeah. Well, I think what we need is basically that kind of collaboration between theorists and empirical research to really take the theory and make it testable in a way that somebody can actually do. And, with the advances that we have now with optogenetics, it's really amazing what people can do. People can test theories in a way that just wasn't possible before.
Mm-hmm.
Like for this theory, you need to be able to disrupt, a particular pathway, or, disrupt a particular channel in these circuits that gives rise to the timing dynamics, various very, very precise kinds of manipulations. Whereas before it's like, let's cut it out and see what happens, And so being able to manipulate the system at a fine grained level like that is essential for testing these theories. The other thing I'll say is that a lot of these early theories, like Francis Crick, for example, has a very famous paper on attention and the thalamus that was based on anesthetized data from anesthetized animals. And what I've seen in the last few years is a huge overturning of a lot of prior literature that was all done with these anesthetized animals. And the behavior of neurons is extremely different in the kind of awake state versus the anesthetized
Shockingly,
state.
yeah.
Shockingly. Big surprise, right? At some level. But people never really appreciated that. And so, a lot of these kind of, especially like the bursting dynamics are really absent. The downstate, upstate dynamics are really absent in the waking state. And so a lot of the theories that people had built up kind of were based on the wrong data in some sense, because they only really apply to these kind of phenomena that don't really happen, in the relevant state when we're actually awake and thinking. So you do have to kind of, everything's always a process of kind of, figuring out what the right data is and not getting too attached to data that might be the wrong data. So a lot of theories like Crick's theories, especially about these attentional things, I think are basically have been invalidated because of these results. And so,
I mean, another loud cry, or at least in my neighborhood of hooligans, that I don't know how loud it is amongst, the rest of the field, is that, speaking of the right data, is that, that behavior is much more important to than we previously realized. Ecologically valid behavior. Right. And that behavior can tell us, some people go so far as to say that behavior can tell us more about the brain than the brain can tell us about the brain. And that gets thorny. But so Leabra itself, and we can always come back, we can just jump around, which is fine. So Leabra itself is, it's not a robot. It's a cognitive functioning neural network based cognitive architecture, but it's not embodied. Right. I know you have plans to embody it. So I'd like to ask you, because I'm going to have Chris Eliasmith on the show in a few weeks here, and he hates you, by the way. No, I'm just kidding. But nice. We're going to talk about Spaun, his cognitive systems architecture, and I wanted you to kind of compare Leabra and Spaun as a preview for that.
Oh yeah, for sure. And I think there's a lot of commonality, and therefore, a lot of opportunity to draw kind of key contrasts. Spaun, I think, does have that advantage of being something where you have a lot of control over what the system does. And a lot of what they've done with the architecture is kind of configure, really building on work that Tony Plate did in the 90s, these holographic reduced representations to solve the binding problem, to do kind of, fairly complex, elaborate forms of cognitive information processing. And so I think they're able to get a lot of functionality out of the system because essentially they have a lot of control over what's happening.
Oh, yeah.
And whereas in Leabra, we're more at the mercy of like, what can we train the system to do and what kind of dynamics are going to emerge as we try to train these systems. And so we have a lot less control. And so I think we can't, they have like models of doing like Raven's progressive matrices and lots of complicated kinds of tasks. On the other hand, those models also provide then kind of perhaps less insight into how the brain really does it, because it's kind of reflecting more of an information processing kind of prior assumption about how it could work. And one question I would ask about these models is, how much have you learned in making that model relative to what you kind of came in with it? Like, how much did the model teach you in making the model? Because I feel like once you have a framework where you can basically get the model to do what you want it to do, that's nice, but it also means that the model has less opportunity to teach you something that you didn't otherwise, kind of know.
About the brain itself, or about the functioning of the brain?
About the brain, about how that cognition actually might work in the brain. I don't feel like the model of Raven's progressive matrices, for example, that they have gave me a lot of insight into how like the brain might actually solve that problem. Likewise with other models that we've seen in AI, where they are now also taking on these Raven's progressive matrices tasks, which are kind of one of the classic tests of general intelligence, and that's why they're very attractive to model with these kind of AI models. But the whole thing about it is that it's a test of your on-the-fly ability to solve these kind of novel problems, and yet they're training these models or hand configuring these models kind of in a special purpose way to solve that task. And once you do that, it sort of negates the entire point of the task, which is that it's supposed to be a transfer task, a novel task that you've never done before. And so it's like, yeah, I can get a system to solve that task. That's not the problem. The problem is, how do I get a system that's never done something like that before to figure out how to solve the task on the fly on its own, and that's the real problem. And again, I think that's where, having kind of introspective access to, okay, well, gee, how am I going to solve this task? Well, I know there's these patterns, just that whole process we would introspectively go through in thinking about how you would tackle a new task. That kind of flexibility, I think, is what's missing.
Good. That's good. I'm going to play your clip there when I talk to Chris. You'll have the question.
Yeah.
And don't tell him.
The other question to ask. Yes. Yeah. Don't tell him. I won't tell him. The other question to ask Chris is, do they clearly explain that the spiking is added on after, like, you program the model using dynamic equations, continuous dynamic partial differential equations, and then they kind of add on the spiking afterwards. And when I learned that, I was kind of like, because he, in his talks, he makes a big deal about how it's a spiking network.
Right.
But it's kind of first a not spiking network, and then it becomes a spiking network kind of after the fact. And so to me, that sort of was like, okay, well, how much is really different between the spiking network and the original kind of, differential equation version of the model? So anyway, you could ask him that.
All right. Shots fired. I like it. One of the things about Leabra that you've built in is you can flip switches and turn on biological realistic details and turn them off depending on how fast you want it to run and what you're concerned with.
Yeah.
I mean, what has that taught you? What I want to know is, like, what building Leabra and the overall large perspective, what has it taught you? I mean, you're wondering what it's taught Chris, what
Absolutely.
Spaun has taught Chris.
Yeah. And that's where I think, again, another major question that we're wrestling with in the lab right now is about spikes.
Ah, okay.
And I think one of the big limitations that we've learned is in scaling up these models, that you get an interesting kind of a heat death. People talk about, like, as the universe ages,
Yep.
there'll just be this increase in entropy, and nothing interesting will happen. And the same kind of thing happens due to the law of large numbers as you scale up these networks, that they really thrive on kind of randomness to select subsets of neurons to encode, some piece of information, one face versus another face. And as you scale them up and you have this law of large numbers, basically, statistically, if you have 10,000 different synaptic inputs, the standard deviation of like how much input you got from one pattern versus another pattern shrinks to the point where basically every neuron is sort of getting some pretty similar overall level of input. And it's very hard to sort of choose like which neurons to represent one face or another face. And that's that scaling problem intuitively seems like something that adding noise, right, in the form of all the noise we associate with spiking, would solve. That there's a sampling process taking place, that the neurons, in some sense, the synaptic weights are representing some kind of probability distribution, but that the active process of activating the neurons and information flow in the brain is kind of like a statistical sampling process, sampling from some larger distribution that's encoded in the synaptic weights.
This goes back to constraint satisfaction and Boltzmann machines again, really. So
yes, exactly. So the Boltzmann model is exactly that. It's a sampling process, and all the Bayesian models with the particle filters are also these sampling processes, Gibbs sampling, et cetera. And so somehow we're totally missing that in the Leabra model. It's great for working on small scale models because they're very deterministic and easy to work with and things like that. And again, we have these switches, like you say, and we could turn on spiking, but every time we turn on spiking, it doesn't quite work.
Shh. Yeah.
And so it sort of works, but it's like it doesn't learn as reliably.
Okay.
And so I feel like we're missing a critical element there in bridging down to the level of spiking. And that once we have it, we may then have, a better ability to scale up the models. And this is another case where the work in AI has also really kind of shined a light on a computational principle that we think also relates to this, which is in the form of these things called variational autoencoders. And there's been a lot of interest in these, and they are, again, a Boltzmann-like kind of sampling process that operates in a neural network. And when you do that, they actually generate much more kind of systematic, generalizable kinds of representations. So there's some hints there that really figuring out exactly how spiking works and capturing that, again, in a way that integrates with our learning mechanisms, which is the key thing, then we could really kind of take things to the next level. So that's the goal.
Is it important to you to get to spiking, or would you be satisfied with a solution that didn't involve spiking?
Yeah, and it's kind of like the thalamus. Like, I wouldn't want to just add the thalamus just so I could have a box on my model that says thalamus. I want to figure out like what computational function that those spikes are actually doing, so that, when I put it in, I know like, okay, we are having spikes not just because they're there, but rather because they're doing this exact kind of computational function. And so that's where I think some of these insights about, the sampling process and the scaling give us a clue as to what the importance of the spikes are. And then we can kind of connect it with the computational story and the biological story and build those bridges.
I mean, what has playing with the biological realistic switches on and off, what has that taught you about, functionalism and multiple realizability, and what actually is important, in AI and in simulating a brain?
Right.
Any major takeaways?
Yeah, I mean, the extreme version of that is like, we have this collaboration with the folks doing ACT-R models.
Yeah, that's another cognitive systems architecture.
There you have a very high level kind of description of what's happening. And I feel like, also going back to your question about behavior, that's a framework that almost exclusively, is constrained by modeling actual behavior.
Right.
And they also came up with this constraint about timing, that, for example, the basal ganglia has to essentially update every 50 milliseconds. And it turns out that 50 milliseconds is the beta rhythm, and the basal ganglia oscillates at the beta rhythm.
Gate kind of thing?
Exactly. Yes. So the opportunity for gating in the basal ganglia essentially opens up at this 50 millisecond time frame. And so, that's like a coincidence that's too perfect to ignore, I feel like. And so I do think that, yeah, you can learn a lot from behavior, and you can learn a lot from these large scale models. And just saying, like, from if you have something that's like a basal ganglia, which they do in the kind of production firing, and you have these maintained kind of goal states, and you have declarative memory, how do those macroscopic kind of architecture level elements kind of work together to do cognition? That's something that's really hard to address at a more biological level, right?
Mm-hmm.
Because the models that you're working with are so, they would have to be so large scale and so complex and so hard to understand, that having that kind of much more compressed, simplified framework allows you to kind of get to the essence of the information processing and the division of labor among those systems. So I think it's essential. I mean, I think I'm a big advocate of multi-level modeling, just like there is no one right model, even though we try to hit a middle ground with our models. Like you're saying, we have switches that allow us to kind of go up and down a bit. And sometimes when you go to ACT-R, I actually coded up ACT-R in our simulator.
Okay.
Because I wanted to be able to, first of all, understand it. And, coding is how you understand things, at least for me. And then I also wanted to be able to kind of go back and forth with these ACT-R models, understanding the overall information flow kind of dynamics, and then try to relating those, and maybe even kind of swapping parts of it out with like a Leabra model where the rest of it is an ACT-R model, that kind of idea.
Has building the models it's kind of from the ground up, because, at bottom, they are connectionist neural networks, right? And has simulating at that level, has that changed the way that you think about any mental functions? Or is it always, here's working memory, and we know we have working memory, quote unquote, and we're going to put it in, and then we put the network in? Or have you ever had the experience of running the model and maybe you've added a new function or something, and then, I don't want to say emergent, but there's some new property that makes you think differently about some mental mechanism, some mental function? Does that make sense?
Absolutely. Yeah. I think the biggest case where that happens, and this happened to me multiple times, is with these kind of binding problems, which come up a lot when you start to think about kind of, again, these larger scale architecture level models. You think about this part of the brain represents X and this other part of the brain represents Y. And if you just kind of have that large scale compartmental kind of understanding, you always have this problem of like, well, how do you coordinate? How do you bind those representations across these areas? And there, when you run like an actual learning model that uses distributed representations, a lot of times it just kind of solves those problems kind of along the way. And by virtue of the kind of high dimensional nature of distributed representations, it can kind of have both systematic and kind of idiosyncratic elements represented in these very hard to imagine high dimensional spaces. And I think that's where, again, our limitations of imagination, like if we just think in terms of these really simple symbolic, like, separated elements, these binding problems seem like a really huge problem. But when you actually like think, and it's very hard to think in terms of these high dimensional spaces, those binding problems in a lot of ways can kind of go away.
It's kind of makes it a robust system almost.
Yeah. And so I do think that's a good example where, running the model kind of avoids problems that you thought you were going to have and that you would have had and that you do have if you just kind of have these large scale schematic models. And I think there's an example of this in, there's a recent paper that was kind of a manifesto by some computational folks saying, here's what's wrong about neuroscience. I forget, I think maybe Richards is the first author.
Oh, there's the Blake Richards backpropagation in the brain. There's the John Krakauer, we need behavior. Okay, yeah.
I think it's the Blake Richards one. I'm pretty sure that's it.
There's a lot of here's what's wrong with neuroscience these days. So
yeah, exactly. So, but I think the thing about that Richards paper is, it's like neuroscientists are asking these very local questions about individual neurons, right? And the computation is distributed, first of all, okay, and also kind of governed by these learning processes. And so if you think about like, what is the system learning to do, and how is the information being transformed across these distributed high dimensional representations, you get a very different picture and you ask very different questions than if you're just like saying this individual neuron has to code the task relevant information in its own single individual neural firing. And I'm going to try to understand how the brain works, neuron by neuron. I totally agree that you can't understand how the brain works neuron by neuron. You really have to understand these distributed representations. Yeah, well, I mean, neuroscience, it's like Hubel and Weasel, right? I mean, it's like that's the techniques that were available.
I think I feel defensive because I was a neuroscientist, but I hear these arguments and I think, who actually thinks that? Like who thinks that? I mean, so just to be clear, that the paper is a deep learning framework for neuroscience.
Yes.
So this is like using the deep learning ideas.
Yeah. But as to who thinks it, it's maybe not that people actually think it, but it was kind of also, again, this thing about the techniques, right?
Yeah.
So if you can only record from a few neurons, that's all you can do, right? And if the story isn't really amenable to being told with a few neurons, then it's kind of like a mismatch between the techniques and the kind of explanations. And you definitely see now in the field of neuroscience many papers that are looking at population level information encoding and telling, I think, a much clearer story at the population level than at the individual neuron level. So I do think it is something that people, it's a technique limitation. And then, the field is kind of, now that there's the ability to record from all those neurons, now you're seeing, the same kind of representational similarity analysis kind of techniques, and all these similar kinds of techniques are now being used across models and neuroscience.
Yeah, that's a good thing.
Yeah.
I went from grad school recording one electrode, putting one down at a time. And then even in my postdoc, we started with a tetrode, so that's 4. And like every 2 months, we'd have to like switch out our systems because there'd be a new electrode with even more and more. And this is so frustrating, really, to get anything done in neurophysiology. You must have you ever made any mistakes with Leabra? What's the biggest setback that you've had with Leabra?
Oh gosh. Well, one just, massive mistake. We had the activation function, the core thing, like about how does the neuron fire, was totally wrong. So, my understanding, again, from like grad school neurophysiology classes is, you take the excitatory current and the inhibitory current and they integrate and they produce a membrane potential, right? And then when that membrane potential gets over threshold, the neuron fires.
Sure.
And so that's how it works. And so I said, well, if I'm going to make, again, a rate code model, because I didn't want to deal with spikes all the time. So I make a rate code model. I based my rate code on the membrane potential. Okay. And it turns out mathematically, unbeknownst to me, that basing a rate code model on the membrane potential is actually the wrong thing to do. It's not monotonic with respect to the actual kind of rate of firing, it turns out.
This is one way that I know in one version of spiking neural networks, this is one way that backpropagation has been implemented by using the gradient of the membrane potential. So I don't know how that relates, but interesting. Yeah.
I'm not sure
so it doesn't.
That. Yeah. So we basically had a non-monotonic activation function there for many years that was, broken in a lot of ways, and later discovered basically that, there is this more linear relationship with the excitatory conductance relative to a threshold that incorporates the inhibition, and that produces a activation curve that fits kind of what spikes actually do. So that was like a big bug, it's like, just a mistake right straight out.
How long does it take someone to go to the website, which I'll point to, and get up and simulating with Leabra? How long would that take?
Well, so one thing is we have a whole new framework now. So we had previously a whole kind of C++ based, more like a kind of like a word processor, kind of like a system where you would kind of create the model in a GUI interactively. We've now switched over to more of the typical kind of every simulation is a separate program using a library. And you can now do that in Python, calling our library. The library itself is written in Go, which is this fun language that I really love that was invented by Google. Yeah, so basically, you can download stuff immediately and run it. And if you're using Python, we have a textbook set of simulations that go with our textbook that has all the executables, and you can just download it and run it directly. So we teach this class, to undergrad psychology majors and everything. And so that has the kind of nice GUI still where people can kind of access the models in a more point and click way when they run them, even though they're still kind of coding them as a program, under the hood. And that's always been a big priority for me in terms of, balancing the research with the teaching, having something that gives people an easy way to access the models. And I'm also a very kind of visual person, so I like to see my models running.
Right.
So one of my goals is to actually use this kind of visualization stuff for like the PyTorch kind of backprop models as well, so that I can actually see how those models kind of work at a more visual level. And I'm always kind of amazed how much the field in AI is just kind of running these models almost like black boxes, and they never look at them and they don't know what they're doing. And I feel like, how do you know what your model's doing if you can't see it? But some of them are so complicated, I'm not sure if it's going to work.
It's going to be rough, yeah. But so how long, if I'm comfortable with Python, let's say, how long would it take me to feel like I've done something in Leabra?
Yeah, I mean, it's a gradation, right? So you can pull up a model, modify it, very easily. You can kind of see where everything's taking place, to actually kind of like master it and be like able to say, I want to take a new cognitive phenomena and, apply a hippocampus and a cortex to it. That's going to be several months to a year or something. Okay. So yeah.
But I could do it in a day. Yeah. I can get a simulation running in a day. Yeah.
For sure. Yeah. It's very quick. Yeah.
Is it silly to ask you about AI consciousness? I know that you associate consciousness with human. Are only humans conscious, or is it just such a specific flavor of subjective awareness that you restrict it to human?
Yeah, that's the thing, is I think it's because we only have one reference point, which is our own subjective experience. We have no real way ever to understand what the subjective experience of another brain is like. And so it becomes very difficult to ask the question and to answer the question, because we'll never be inside another brain. And so you can never know. And so you can speculate, and you can do these kinds of correlations of like what properties of brains seem to be important for what kinds of overt behaviors. But fundamentally, this kind of Chalmers hard problem, this duality, this divide between, what we can characterize objectively versus what we can actually subjectively experience, that barrier prevents us from really saying, this other thing is conscious in some way that we can really be sure about. So I think we're going to have AI that's conscious.
Oh, okay.
Everybody's going to be like happy to say, yeah, that thing seems pretty conscious. It's expressing subjective experiences in a way that, we can relate to. And again, I think that would be a situation in which we had essentially done a pretty good job recreating the human brain.
Yeah, so you're not that much of a functionalist that you could do it with a water clock set up the right way.
Right.
Okay.
Exactly. You could have other things that have other kinds of subjective experiences that are rich and complicated, but if we can't subjectively relate to it, then we won't really know what to make of it, and maybe there'll be like this whole different way of having consciousness but that thing will be able to explain and translate its experiences into a terminology that we can understand.
Mm.
And then maybe we would sort of vaguely understand kind of what's going on in that other thing. But we wouldn't be able to have that qualia like, oh yeah, this thing is feeling sad in a way that I feel sad, that kind of direct ability to understand what that means.
Well, I know you're going to be sad if I don't let you go in a minute, because you need to you're not Leabra or AI, and you have to put food in your body and play with your children, with your kids, with Legos. But my last question is, and thank you very much for your time. If you were going to go back and begin again, like right now, how would you proceed? That's a huge question for 30 seconds or whatever, but.
Absolutely. Yeah, it's really interesting. I think there's so much available right now in terms of, all these, training courses, and people can learn a lot of core principles of AI and statistics and just all this amazing stuff, programming languages. So I feel like we have all those resources available. And, for me back then, it took a long time to sort of, learn all that stuff. So I feel like there's a great opportunity to sort of, quickly, efficiently learn all the kind of basics. But fundamentally, finding a lab where people are asking the same kinds of questions that, you resonate with. And for me, it's still the same questions. Like, how do we understand how the brain works? And so I wouldn't necessarily go back to Jay McCullen's lab now, because, that was then, this is now. But I would seek out those same kinds of experiences. I feel like grad school was amazing. I really like academia. I like the freedom. I like the ability to kind of, explore the questions I want to explore. So even though, the competition level in academia is much harder now, I would probably at least give that a try and see how it goes.
But you wouldn't do neurophys lab. You'd go computational.
I think I would stay computational. It's hard. I feel like we're going to get all the answers from neurophysiology someday. Someday is a long time, maybe. And I feel like if you want to get the low hanging fruit, you can still attack a lot of questions computationally quicker. And you don't have the certainty. You don't know if you've really answered the question, but you do have at least the ability to kind of address the questions computationally more quickly in a way that suits my impatient personality.
Yeah, so, it's still a slog, but it is faster than. Everything's faster than neurophysiology. By the way, Jay says hello. He didn't submit a question for you in time. I thought that would be fun, but your old advisor, Jay McClellan, says hello, and he's interested in your motivation work, which we didn't get to. But
I need to connect with Jay again. I haven't been in touch. It's really been tough moving here to Davis with all this. All the moving the whole lab and everything and getting rebooted here. But
Well, continued success and thank you for your time. And I appreciate it.
This was really fun.
Brain Inspired is a production of me and you. I don't do advertisements. You can support the show through Patreon for a trifling amount and get access to the full versions of all the episodes, plus bonus episodes that focus more on the cultural side but still have science. Go to braininspired.co and find the red Patreon button there. To get in touch with me, email paul@braininspired.co. The music you hear is by The New Year. Find them at thenewyear.net. Thank you for your support. See you next time.